Welcome to iSecurity, an IoT platform that allows you to manage the safety and security aspects of indoor public places. You can see here the general architecture of iSecurity. The system is composed of a set of sensors and actuators, integrated into a unique cloud environment by exploiting REST and MQTT web services. Now we are going to analyze more in depth the iSecurity main components. Let's start from the catalog.
This is the catalog code that serves as a web server to obtain information and manage all devices, users, and services of our project. Technically, it is a cherry-pie managed web server that exposes the catalog class to the address and port defined in the configuration file. The init of this class creates a data structure called self.cat containing all the useful information. Immediately, the program tries to open a backup file previously saved. Alternatively, if the file is corrupted or not existent, the catalog will create a new data structure. Finally, the init creates two threads. The first is to delete all devices that no longer send data after a time interval defined in the configuration file, while the second one saves all the information contained in the catalog in a backup file that will be used to restore the catalog in case of a crash. The methods you can access the web server are get, put, post, and delete. Get method allows you to get information about the broker devices or a specific one to be searched through the appropriate pattern. All users, a specific one. Services, all the catalog or freeboard. The post method allows you to add a device, user, or service to the catalog. This must be accompanied by a body. This body has to contain all the necessary information. The catalog will only add the information about the timestamp to which the action was performed. The put method, instead, allows you to update devices or services. As soon as new information is sent, the timestamp of this data is updated. The delete method allows you to delete all users, devices, and use services identified by the id parameter. Information and examples on how to read and make requests to the catalog are contained in the beginning of the script.
Now instead let's analyze the hardware part of the system. The sensors are all physically connected to the Raspberry Pi and they are managed by a single library called devicelib. The devicelib is a Python library that provides an abstraction of all the hardware devices present in the iSecurity system. It is composed of 7 classes, one for each type of device. Let's start with the first one. It deals with the temperature measurement of the Adafruit-DH11 sensor. When a temperature sensor object is created, it needs as input 3 parameters. Local ID specifies the local in which the device is installed. Device ID is used to enumerate devices of the same type. Pin list provides all the pins to which the device needs to be connected. The fundamental function of the class is the measure function. When called, it tries to get a measure from the hardware, then fills in a SNML message with the current time and temperature. Eventually, the message is returned as a JSON. The second class of the devicelib is very similar to the previous one. It deals with humidity measurements, using the same idea that worked for temperature. The class motion sensor provides an abstraction of the DSUN infrared sensor. The hardware device shows some limitations. When it detects a movement, it gives 1 as output for at least the following 3 seconds. To avoid repeated unwanted data, the measure function returns 1 only one time, then 0 for the following seconds. The door sensor is based on 2 coupled motion sensors. As for the temperature and humidity sensors, it is characterized by 3 parameters: local ID, device ID, and pin list. The class implements a thread-based algorithm to detect the activation of the 2 motion sensors within a certain time frame. If the outer sensor is activated before the inner one, an entrance is detected and the counter is increased. By converse, if the inner sensor is activated before the outer one, an exit is detected and the counter is decreased. By means of this counter, the device keeps track of all the people passed through the door. Due to the hardware limitation explained before, it is assumed that at least 3 seconds pass between 2 consecutive events. The measure function, in this case, simply returns the JSON SNML message with the updated counter. The following 2 classes respectively model the MQ2 gas sensor and the DF robot vibration sensor. After the usual initialization, the resource value is set to 1 if gas or vibrations are detected, to 0 otherwise. The measure function once again returns the JSON SNML message. The last class of the devicelib is a generic abstraction of all the possible digital actuators of the system: alarms, LEDs, and relays. A thread continuously checks if the current command is one of the following: on, off, switch, blink. For each one of them, a function implements the control logic using the GPIO library. Instead of the measure function, here we have the control function. It simply extracts the command from each JSON message that is received. Further explanations of each class are provided in the comments of the Python file. As you can see, the connection between the devices and the catalog is managed by the device connector that will be analyzed in the following.
The device connector is the class used to provide the connectivity between sensor and actuators and the IoT platform. When the code is executed, the configuration file is read. From the information present in that file, the right device ID and MQTT topic are generated. Then, the sensor or actuator object is instantiated from the device lib, passing the Raspberry pins found in the configuration file. The MQTT object is created, getting the broker IP and port from the catalog. Then the device registers itself to the catalog, writing all the needed information on it. Now, a special thread is needed, the timing thread. This is simply a thread that calls at regular intervals a specific function. If the device is a sensor, a timing thread is created to call the send function that simply invokes the sensor measure function and publishes the collected data on the MQTT topic. Another timing thread is created for both sensors and actuators in order to call periodically the still online function that performs a put request to the catalog to notify that the device is correctly working. The notifier function is used only by the actuators and is automatically called by the MQTT object when a message is received on the right topic. The message is passed to the control function of the actuator that will decode it and perform the right action.
Now let's have a quick look to the control algorithms that allow the user to detect and tackle many different critical issues.
Control algorithm is the general class common to all the other control algorithms. This class is mainly used to read the configuration file, get the broker and the port, get the topics for the publish and subscribe from the devices, and finally to post on the catalog the services provided by each control algorithm. Temperature, humidity, gas, and vibration control algorithm have all the same structure. Consider temperature. We receive a CNML message containing the value of the variable under control. This value is compared with a reference value taken from the configuration file. If this condition is verified, we publish on to activate the alarm, otherwise we publish off. The difference between temperature and humidity with respect to gas and vibration is that gas and vibration receive a binary values, 0 if the situation is under control, 1 if the situation is critical. Quantity people control algorithm checks if the number of people inside the room is below the maximum allowed value. We receive the counter of the door. Then all the counter we receive are inserted into a list. Then we sum all the counter inside the list. The result is compared with the maximum allowed value, and then we publish on or off.
Eventually, let's deal with the last core component of iSecurity, the data receiver. The data receiver is a Cherry Pie web server that is able to collect and store all the data generated by the iSecurity system. After the initialization of some parameters from a JSON configuration file, the receiver registers itself to the catalog. Then, the main dictionary in which all the data will go is created. The following functions collect the topics of all the online devices and start the MQTT connections. When a message arrives, the notifier function appends a new entry to the main dictionary of the data receiver. The keys and indices are automatically built starting from the topic of the message. Each entry comprises a measure and the time at which that measure was actually taken. Next, a series of threads allows the user to save data to a JSON file, eliminate all measures, and check for new devices at intervals specified in the configuration file. The data receiver exposes a get method, through which it is possible to extract the last data of a certain device by entering the corresponding URI. This method is used by Freeboard to update in real time its graphs and diagrams. The user interfaces, such as Telegram and Freeboard, are all connected to the data receiver and will be shown during operation, together with all the other components, in the following live demonstration. First of all, we start the catalog on a PC and all the devices on the Raspberry Pi. The devices now are registered and start collecting data. Then the control algorithms, the data receiver and the Telegram connector are launched. The system is ready to work. Let's see some control algorithms in action. Here the sensor detects vibrations, and the respective control script responds activating the alarm. The same works for the gas sensor. When gas is detected, the control algorithm receives a message on the gas topic and reacts publishing an on message on the alarm topic. Here you can see how the iSecurity system can monitor the number of people present in a room. Each time someone goes through a door, a counter is increased or decreased. Making the algebraic sum on all the doors, we can find the number of people inside the room. If this value is higher than a certain threshold, the control algorithm activates the alarm and sends a warning message on the Telegram bot of the users. Then, when someone goes out, the alarm turns off. As regards the actuators, here you can see that it's possible to remotely lock and unlock some doors using the Telegram bot. Eventually, let's take another look to the Telegram bot and to the Freeboard interface. The Telegram bot allows you to log into iSecurity by choosing a user ID. Then several different operations are possible: retrieving the catalog and the broker IP, finding all the online devices, getting specific data from one of them, and so on. In the meanwhile, you can see that the Freeboard interface lets the user to dynamically visualize all the data collected by the system in the form of graphs and diagrams. Thank you for watching and for choosing iSecurity.